Hello and welcome back. We now take a closer look at clustering. Clustering is an unsupervised machine learning algorithm, and essentially it's about grouping data into points or clusters. And the distinction between them is that all the points that are part of one cluster are closer related to all the other points that are in different clusters or outside clusters. So that necessarily implies that we need some sort of metric that defines how closely related some points are. We now go through a number of different clustering algorithms and look at their properties. There is not just one algorithm, but several different approaches, and each of these approaches have their specific advantages and disadvantages and behave in different ways. To illustrate the point, we will create three artificial data sets. There are blobs. This is essentially a scattering of points. Then we have moons and circles. So we import all the relevant libraries, and scikit-learn, the machine learning library, not only provides us with the algorithms for the clustering, but also with a convenient set of functions to create these artificial data points. So we start with generating the blobs, and this is essentially our ground truth. So we have three clusters indicated by the colors here, and we generated them so that they're both well separated, but also have some overlapping areas, and we will investigate how these clustering algorithms perform on these data points. The half moons are this, and you can see that this is quite different. They are well separated clusters, only two of them here, but if you have a projection in X and Y direction, they would completely overlap, although in the plane they are well separated. And circles are sort of a bit more advanced. Of those, we have an outer circle and an inner circle. Now we look at how the different clustering algorithms behave. Clearly, for all of these cases, we can define already by eye that, for example, the blue points are much closer related to each other than, for example, to any of these orange points. So visually, for us, it's obvious which points belong to which cluster. Now let's start with one of the simplest ones, the k-means algorithm. We have here the code to run it, so we create an instance of the class that is part of the machine learning library, and then the scikit-learn interface is always classifier or machine learning algorithm fit, and then we use it to make predictions with the predict method. And then the rest of it is more or less a plotting magic. So we put the ground truth on the left and the algorithm on the right, and we can see that this behaves fairly well. We can separate the blobs, and of course on the borders here and here we don't expect it to perform extremely well, because how should the clustering algorithm know that this black point, for example, is indeed a black point and not one of these clusters? Now we do the same for the half moons, right? Again, we instantiate a new algorithm and call fit and predict, and now we do it on the dataset with the moon. Here's the plotting magic, and you can see the algorithm doesn't really perform at all, right? It generates the clusters and it doesn't capture at all the specific relationship between those. And as an exercise, you can do the same things for the circles. One more performant algorithm is called dbScan. It's density-based spatial clustering of applications with noise. And then this is designed to find clusters in data with noise. So this is quite advantageous in real-life situations, because we will inevitably always have some noise in our data. And unlike k-means, it doesn't require that we know the number of clusters beforehand. However, you need to set the hyperparameter epsilon and some others. And essentially, these hyperparameters control how the algorithm behaves and the maximum distance when we define, for example, the neighborhood of a sound. The code we use here was taken from the scikit-learn example, because they have a nifty way of showing the output and the clusters themselves. So this is why the plotting magic is much more involved, as we have done previously. And you can see that when we put it onto the blob data set, it found 6 clusters with this a parameter of epsilon. If you vary the epsilon, then you will find a different number of clusters. So one of the tasks when you work with this algorithm is to tune this parameter. And you can see that the clusters are fairly well separated, and we just have these three sort of satellite clusters. And this is what we mean by noise. These black points here, they're not associated with the clusters because the algorithm thinks that they cannot attribute them properly to any of these. So we can see these big blobs are fairly well separated. And now we would have to decide how we deal with these satellite clusters. For example, as an exercise, you can go through and now change this parameter and see what happens. Then for the half moon, we see that this algorithm is perfectly well capable of capturing this data, and the same holds for the circles. Another approach are Gaussian mixture models. This algorithm is somewhat similar to k-means. It requires that we set the number of clusters. This is the main common ground. As we said above, the dB scan doesn't require us to do this. So when we use either the Gaussian mixture models or k-means, then we need to have some sort of expert or domain knowledge that determines how many clusters we look at. And Gaussian mixture models are essentially working that we create a number of Gaussian functions to capture the essence of the clusters. And again, we call the fit method and the predict method. Note that we can also chain these together. So here we create an instance that fitted directly. For the blobs, we can also see that it behaves quite differently to dB scan, but very similarly to k-means. It's essentially the same picture. And you can also see that the Gaussian mixture model has the same problems as k-means in this half-moon data set. And if we do it for circles, it's even worse. We can compare how k-means and the Gaussian mixture models differ in their assignments. So we run both of them and plot the difference between them. And you can see that essentially the k-means and the Gaussian mixture model have the same assignments apart from very few data points here